Yeah, so MX3D had the opportunity already to cross the path of the ESA, the European Space Agency, several times. And if Corona permits, we will have a really nice project to show for in a couple of months' time. I'm looking forward to that. But in that in these contexts, I didn't meet Dr. Engineer Chiara Manfletti yet. She is the program advisor to the Director General at the Space Agency. And she's going to be our next speaker. Yeah, I mean, she has the enviable position to help out to determine the goals of the future ESA space projects. I mean, who wouldn't want to have that job? Sounds like a really nice place to be. Um, so, a very interesting long resume, educated at the Imperial College and the International Space University in Strasbourg. She collaborated with NASA and the German Aerospace Center, DRL. And she's the president of the Portuguese Space Agency. Besides her strong engineering skills and focus on space propulsion systems, she also likes to do beekeeping and has a basic knowledge in Japanese. But no mention of 3D printing. So fortunately, I saw the Beam book where she does go deeper into her 3D printing interests as well. But I'm very curious to see what she can present for us today. So over to you, Chair.
Thank you very much. It's true. I do not have a background in 3D printing. I am a liquid rocket propulsion engineer from my experience and what I've done. And so, what I am actually going to share with you today, and good afternoon, everyone, is what we at the European Space Agency have been working on over the years. I'm not necessarily the expert, I also have a couple of names, and I'm hoping that you're all seeing the slides. Um, you seeing the slides? Can someone just give me a quick
Yes,
confirmation? Perfect.
yes.
Okay.
Perfect.
So thank you very much. So you see here all the names also of my colleagues, Tommaso Ghedini and Jérôme Breteau. One of them works in the materials part of ESA. The other one works also in liquid rocket propulsion and in space transportation. And if you should have any also detailed questions about specific projects that we've done, please don't hesitate to write to them. You see that email is just first name dot last name at esa.int. So it's very simple. As I said in the presentation, I'll be sharing some of the things that we do at the European Space Agency, but just a quick introduction of what it is that we do as an agency. We are an intergovernmental agency which actually pushes forward industrial policy interests of member states, meaning that member states define high strategy lines that they want to be implementing in space, and they try and do this together in a European spirit, and for that they need us. We have 22 member states spread across Europe, meaning that if at any stage anyone listening is interested in working in space, then certainly we could have a talk, and then we would also have to have a chat with the delegates of your respective countries to see how we could bring things forward. Now, at ESA, and why am I showing this slide? I'll get to it in a second. We have the ambition, of course, of serving society and of serving the economy. As I said, there is a strong industrial policy component in what we do, but we are extremely keen on serving also the environment. And when I talk about the environment, it's not just our environment and the sustainability of things that we do. And I do think that 3D printing and advanced manufacturing certainly go in that direction, but it's also about in space, right? And when we talk about debris, when we talk about also going further, sustainability is a key from also certainly a financial point of view. Going to the moon the way we did back in the days would not necessarily be considered sustainable, and that's part of the reason why the Apollo program didn't continue. So now we don't talk about going back to the moon, but going forward to the moon in a sustainable way. We do this through different roles that we have, meaning that we engage in R&D elements, but we also have public-private partnerships with industries that believe that their product is more advanced and has a strong business case to it. We try and be a customer wherever we see that there is a possibility to do so. But we have also testing facilities where SMEs and researchers can come and use these facilities, which otherwise would not be available to them. And sometimes we just act as brokers. So don't hesitate, again, to be in touch with us for different reasons. Now, in terms of the actual content of what we do and where materials and specifically 3D printing, advanced manufacturing comes into play, this is all of the topics that we deal with. So we're dealing with science and exploration, looking into the secrets of the universe, building satellites and probes that go to different planets and, deep into the solar system, to doing human exploration in low Earth orbit and looking forward again to the moon and then onto Mars at some stage. But we also deal with safety and security. And here, for example, things like space weather is an issue. Radiation levels are an issue again, and this also plays into how we build, manufacture, and the kind of materials that we can put in place. Debris impact is always an element, right? So these are also things that we need to consider in our processes. We talk about, of course, also asteroids, and that brings me to the idea of also in situ resource utilization. And this, again, how do we make use of resources in space rather than bringing stuff from Earth, which already is there's not enough to go around, as it seems. So how do we use the stuff that is in space? In terms of applications, we look at Earth observation, telecommunications, navigation. Here the pressure is, because it's commercial activities, how can we use advanced manufacturing to reduce time to market, reduce costs, and go from, a niche sector where we produce one-offs to, mass market, right? How can we make things faster? In enabling and support, we develop technologies. We have a fleet of launchers that we've developed over the decades. That's actually one of the reasons why ISSA came into being. And indeed, as you heard, there's a rocket equation, and this rocket equation says, let's try and make sure that the structure that you have to use to bring whatever it is that you want to have in orbit is the minimum, and most of the rest is either payload or propellant. So reducing the cost, but the weight of stuff is extremely, extremely important. So, oops, too fast. So in summary, I would say that the things that we look at are access to space systems, right? So our rockets, we want them to be cost effective, payload friendly. There's certain accelerations that the payloads have to go through. It can be, if it's a human payload, we try and to be kind to the humans that are put into orbit and subject them to just a few Gs. But if it's just structures, it could be up to even 10G. There's thermal constraints, there's vibrations, acoustic environments, and then one day we're also thinking of reusability, as I'm sure you've heard if you follow a bit of what we do in space. So how does all of this play a role into the materials and manufacturing elements that we look at? Then we have in-space systems, right? So these are spacecraft which remain in orbit or in space during most of their functional life. Here we always try and minimize volume and mass. Why? Because we have to put it in orbit, and putting them in orbit costs a lot of money. So it's beyond just the manufacturing cost of the element itself. We try and minimize, obviously, power consumption and not violate, obviously, the thermal operating conditions of each component. The trends are that we miniaturize, again, to reduce the cost of access to space. And then, of course, there's planetary systems, which go to other bodies, Moon, Mars, Jupiter, comets. Again, here we try to build small and efficient as much as possible. But we are obviously constrained also by the conditions that we have in the solar system, and sort of thermal day-night gradients, which can sort of happen either when you're orbiting, or can also happen just from one side of the object to the other. And of course, we have the same thing on Earth, but with an atmosphere that keeps us warm. Just as a summary, these are sort of the boundary conditions that we have to deal with in terms of gravitation, in terms of surface temperatures when we decide to look at other bodies. And you can see that the range are very different. So when we think of going to the moon, we have to consider elements that are not just can withstand these temperatures, but and can be sort of operated in these gravitational conditions, but also the processes that we have are compatible to this. I mentioned already the constraints that we have when we launch. Now, just a bit of an overview of what we've done in propulsion. Propulsion is probably one of the most costly elements in access to space and launchers, beyond being, if you will know, one of the most critical elements. Without propulsion, you don't get anywhere, right? So we've started with things which are very small, and what you see here is a very small thruster. It's a 10 Newton, so it's tiny. These are used on satellites, and the combustion chambers and the thrusters, so the nice shiny metal part which you see is that which produces thrust to move the object around. They are normally made out of platinum because of the thermal cycles that they have to go through, and because these structures cannot be cooled. So they're normally using hydrazine. The pressures in them are up to maximum 20 bar. They go through lots and lots of cycles. In any case, in 2015, we had the first 3D printed platinum combustion chamber, which was successfully hot fired in a campaign. Looking again into propulsion systems, we went then higher in terms of thrust. So we went to bigger systems. And here we were working with storable propellants. These are propellants that are liquid at ambient temperature and pressure. So it's nitrogen tetraoxide and MMH. Again, pressures are about 20 bar. What is challenging here, of course, is that the thrust chamber throat temperature can be as high as up as 3000 Kelvin. So the inner structure somehow has to be cooled, and normally we have some cooling channels. So the challenge here again is, how do we manufacture something like this so that the cooling channels remain good enough, and so that the inner surface also of the combustion chamber doesn't cause too much friction, which would have all sorts of impacts on boundary layers and on thermal gradients across the structure. That was not enough, so we then went to the next biggest challenge, which was a Vinci combustion chamber. Vinci is yet another liquid rocket engine. This has a yet higher thrust, 130 kilonewtons, 60 bar internal pressure. But the nice thing here is that it's liquid oxygen, liquid hydrogen. So the materials that, or the fluids that we are sending through the cooling channels and then through the combustion chamber are originally cryogenic, and then of course again the thrust temperatures, the throat chamber temperatures go up to about 3200 Kelvin, right? So it's really, really hot. We use here copper in the inner lining because of its thermal conductivity, which is excellent. And generally we have a nickel lining on the outside. Of course, here the challenge would be how to produce a single structure out of two different alloys, and perhaps even to tailor the alloys such that they are also optimal from a manufacturing point of view in this new manufacturing paradigm. Final example, and near final example, is the biggest engine that will produce in Europe, which is LOX methane. These still remain cryogenic. This is then 1000 kilonewtons. So this is the range of things that we have in the central stage of Ariane 5 and Ariane 6. And here we're looking at very many components that will be 3D printed. So it's not just the thrust chambers as I've shown you so far, but it's things like pump casings, what you see here, and all sorts of manifolds as well. Just to give you a sense of perspective, for an engine which is about between 1000 and 2000 kilonewtons, the turbo pump assembly, basically the pump, the turbine that drives and increases the pressure for the fluids to be pumped in the combustion chamber, where the chamber pressures are of about 150 bar. Each one of them weighs between 500 kilos and a ton. Okay, so these are big pieces. So again, reducing the weight is extremely important. And in many cases, what we also have is, in combustion chambers, we have injection elements. And when it gets to these big engines, we can have as many as 500 injector elements. So being able to produce these so that they don't have to be singly manufactured and singly screwed on also make assembly processes and manufacturing processes a lot faster. And this obviously also drives the cost down. Other elements in propulsion are things like filters, where here we have one that we've produced from a titanium alloy. It's a monolithic design. Again, it's about reducing manufacturing time and cost of these elements. Another thing which is important for us is looking towards not just the material characterization, the smoothness of the components when it comes to fluidic properties and elements, but also how can we, when we also look towards qualification and certification to flight, but also reusability, is how do we have non-destructive investigation and insights into the health of these components after we've used them. So that's certainly another element that we've been looking into, especially looking for, again, upper stage engines, as this one, which you see, which is a subscale element of an upper stage engine, again, liquid oxygen methane for the Vega upgrade vehicle, which is Vega E. We certainly look into also then what we can do for satellites, and I just have a couple of examples here. For example, you see solar panel brackets where the solar panels are attached to the satellites, which are now produced in single pieces rather than multiple pieces, and where they are obviously also designed to have a better structural performance for lower weight. Some things that we're also doing for the structural performance are also linked to the structure of the launchers themselves. Here is another example of a titanium alloy bracket that we've looked into for the Ariane 6, where we've seen a 30% mass saving. And we produce sort of 20 to 30 of these brackets per launcher. And here in this picture, you see sort of the prior, which is on the top right design, to the lower design, which you see is then also designed a lot more to fulfill the functionality of it, and is not just very simple because of manufacturing constraints or reasons. Other things that we've done for launchers is looking at polymeric vent ports for Vega, where again we're just reducing the number of components and therefore the assembly complexity of the things that we do. Just a couple of pictures here of the assembly of these elements then on the launcher itself. Another thing which I find extremely interesting is when we look into the topic of debris. Debris you can sort of do two things with. You can consider recycling in space, and this is certainly one of the topics that we'll be looking into, the whole sort of economy and cycle of materials in space. But when objects come down, demisability is sort of another material property that's interesting for us, because we don't want things to sort of come down and plonk in your living rooms. I mean, it's nice to get some space gadgets for free, but you know, there's some damage that it can do. So how can it sort of break up in the atmosphere? And what you see here, of course, is a design where there's going to be a lot of heat pickup, and therefore it's going to break down very easily as it re-enters into the atmosphere, right? So things like heat capacity, thermal conductivity, density of the material, these all play a role. So we are also trying to lead in how to design for demisability of our structures. And then, of course, we come to the exciting topic of producing in space for space activities. And we have looked at various elements here. You know, we've brought up a couple of printers on the ISS. In the US, they've done, as far as I know, also food printing. So far, we haven't done any of that. But what you see here is, for example, a fused deposition modeling printer, which was on the ISS, an Italian-led project, and where now these components that was printed in space is being sort of cross-checked with something that was printed on Earth to see what the quality was. We also had a 3D printer that was specifically designed for weightlessness and can also print using recycled plastics. Again, we're starting to look into this closed loop reuse of materials, which is extremely important if we want to move forward in space. And this printer was able to print in different directions, and I have a pretty video which I hope you can see. So, in any case, it's managed to produce a couple of things. And again, the idea here is you can't carry up possibly everything that you will possibly need, even as an astronaut fixing things. So, if we can produce stuff in space, it certainly also makes us a lot more flexible in the things that we can do, and it can help us, tackle any challenge that can come our way. Um, Obviously, as I was mentioning, human exploration is what drives our curiosity the most, of course. And the idea of one day, spending some time on the moon, I'm certain has also tickled your imagination. We do certainly look into how we can do this best. It has to be sustainable from a resources point of view, but we also have to make sure that we protect the astronauts that move, that are on the moon and go towards the moon and even Mars. And I've mentioned already the item of solar radiation. We have to also protect them from meteorites. So being able to print structures on the moon using resources on the moon or other bodies is certainly something that would help us make sure that exploration is sustainable and also break new boundaries. I'm sure you've heard in Luxembourg there's significant investments looking towards the use of resources even on asteroids. That would be for other purposes as well, but it goes in the same direction. Parallel to this, of course, we're also looking at how we can perhaps go into so-called uh, lava tubes on the moon, so going underground. But part of the things that one could consider that doing on the moon, if we were to able to build structures with the resources there, are even beyond the human elements. In craters, build things like also telescopes that we could use to do excellent astronomy from the far side of the moon, not necessarily the dark side of the moon. Um, so again, the idea here is to cannibalize elements from things that are already there, but also extract things from resources that are available in the on the planets and bodies that we go to, and then of course recycle things that we do. We aim, of course, always then to bring benefit back to Earth, and our ambition, of course, is to make sure that through exploration, then the whole of humanity benefits. Therefore, pushing again for recycling culture, but also supporting in those for example, post-earthquake or tsunami support, where there's also difficulty in continuing sustained life and infrastructure, and then where we have also limited resource manufacturing, like in desert and remote areas. So that's where we think we can also bring benefit back to Earth. I'm sure you've seen this picture. This is where we had tried to make, if you will, a one-off element. We had used a simulated lunar regolith, which we then mixed with magnesium oxide, put in a salt binder to produce a sort of a bee hive structure in order to have exactly these elements that we can consider sort of domes on the moon to protect then the habitats that we would have inside, again, from either solar radiation or things like meteorite. We've also looked into solar sintering using solar light. What you see here is actually a project that was done with DLR. They have infrastructure to do this. This does not require any binder. The project itself was looking both at the design of the equipment and the challenges. And the process, forgive me, and the challenges. Some of the challenges that we, of course, had were the thermal stresses, the fact that we have vacuum conditions on the moon, for example, and of course the actual regolith behavior as it's handled. I was mentioning limited resource manufacturing. This is certainly something that we've been looking into for our elements towards Mars. Some of the difficulties or challenges that we've looked into were the binder ratio, the stickiness of the extruded material, the sagging of the actual extruded material, and again, the behavior in vacuum. We have looked into ceramics as well for planetary settlement. What you see here are some of the elements that have been printed with extremely fine resolutions. Again, this also ties into in situ resource utilization for manufacturing spare parts and electronic components. Finally, what we've also do is we look into extraction of materials from the regolith, be it oxygen, which will help us, and I was mentioning to you the rockets that use liquid oxygen and hydrogen, so we can use it for propellant, for propulsion elements, and I don't know why my thing is moving forward. I don't know if someone's telling me I'm running out of time. So we extract the materials and to see whether we can then again go into additive manufacturing, 3D printing on site for the various elements. Finally, and I think this will lead on nicely to, I understand, the next presentation, the next keynote. We have been looking into 3D printing for bioprinting for human tissue, and this is obviously linked to human exploration. I won't present the slide in detail. This is just to say that we've looked into it, and this is certainly of great interest to us as we look for sustainable exploration and dealing with, you know, if you go to Mars, you can't really go and come back very quickly if you have a medical emergency. So being able to do such things would also help from a medical and human support point of view. So that was it. I hope I was able to give you perhaps not the most detailed technical presentation that you've heard today, but one that was more spanning what we do across ISA in the different domains that are related to space. So thank you very much for listening. And if there's any questions, then please do let me know.
Thanks, Chiara. It's a very interesting presentation. I think, yeah, it's cool to see the different aspects of 3D printing within ISA. One of the questions came up for me is we at least thought about participating in the NASA additive manufacturing challenge to print a dome. And is there anything like a vision at ISA for one of these kind of projects? Because I would say that would help a lot in defining what kind of developments should be picked and prioritized. Because now we've seen quite a few separate projects, but not like this one vision of in 2025 we are going to 3D print a dome on the moon or something like that. Do you think there is something like this?
Well, I mean, we do have different visions. I mean, in the sense that, you know, we member states put a significant amount of money together, right? It's member states alone, it's like 4.5 billion a year. So we can allow ourselves to have multiple 3D visions, if you will, in this 4.5 billion a year. And there's certainly part of it which is linked to launchers, definitely, without a doubt. When it comes to exploration, we are having very strong initiatives, and we are pushed mostly by the Luxembourg of doing in situ resource utilization. We don't necessarily have said we want to print a dome on the moon. This we haven't, but we do want to put, you know, the first boots on the moon again by the end of the decade, right? So that is there, and associated to that is the fact that because we want to do it sustainably, we will absolutely have to look into this. I can look into if we've haven't announced a challenge or so. I can ask my colleagues because I'm not specifically in the exploration program. So I can ask my colleagues if there's a planned challenge or something which specifically responds to your answer, to your question.
Thanks. So I have a couple of audience questions. I'll just read them out. I haven't sort of selected them,
Yeah.
here let's see what's there. Architecture and aerospace have historically always been linked together, albeit aerospace has generally always been a few steps ahead. Do you have any advice for civil engineers working with this new technology? Can you draw up from your successes and maybe fails in this field, which could be useful to bear in mind? So,
Um, so I don't know if we've been up a few steps ahead. This I cannot comment on. I'm not quite sure what the question is aiming at. So I'll try and give an answer, and if it's not correct, then I hope the person will get back to me in any case. I do think that if we are looking at elements for the moon and specifically these things that we've been looking at, architecture needs to be part of the equation, right? From different perspectives. So civil engineering is certainly extremely important for us, and we should touch base with one another. And there's more than enough need for civil engineers to work with us. Now, from the advice that I can give back to civil engineering as such in 3D printing, no, this I cannot. I don't think I know enough of what's going on in 3D printing in civil engineering to give any feedback on to make any comment on this statement as such.
All right.
Again, I'm not quite sure what the question was aiming at.
Yeah,
I'm afraid
it was
that.
maybe a bit generic. So there is another question, and to summarize it, I think the question is whether you have seen interesting projects where the recycling of, yeah, in your case, space waste is being shown as a possibility. So I personally know one from the Dutch Design Week where a designer collects plastic waste and then he shreds it to pieces and then 3D prints a new functional parts again. But I think, yeah, it could be interesting to see if there's any of these projects out there already that have been successful.
Well, I think the Melt 3D printer I was showing to you has exactly this purpose, right? So that was one that I would have showcased today. I'd have to look into if we've have more beyond the ones that you just mentioned. I don't specifically know if we have others. However, I can tell you that recycling and sustainability is a big issue. So if we don't already have enough, I'm sure there will be more coming up, and if there's anyone with great ideas, then please do knock on our doors.
Yeah, I think that's a great invitation to end your presentation. Thank you very much.
Thank you very
And,
much.
yeah,